So a lot of people will probably watch it offline using the YouTube channel of IFIP Performance 2020. All right, so let me introduce our next speaker. I'm just trying to find my notes here. Yeah. So our next speaker is Dan Wang. Dan is currently an associate professor at the Department of Computing at the Hong Kong Polytechnic University. His research interests lie in computer networking and recently in interdisciplinary domains of smart energy systems. He publishes in major networking conferences like SIGCOMM, InfoComm, and also in interdisciplinary conferences such as ACM E-Energy and ACM Buildsys. He won the Best Paper Award of ACM E-Energy 2018 and the Best Paper Award of ACM Buildsys 2018, and he served on the TPC as the TPC co-chair of ACM E-Energy 2020 and TPC co-chair of IEEE ACM IWQOS 2020. With that introduction, I asked Dan to present his slides and take it from here.
Thank you. Thank you for the kind introduction, and thank you for having me. Today I'm going to talk about things related to Internet Industry 4.0. So usually Industry 4.0 are divided into three phases. Digitization, which related to convert signals into digit. The research problems include how to develop low-cost sensors in many industry scenarios, like high-frequency sensors are quite expensive. And there are other problems like signal processing, etc. The second phase is networking and computing, where to store data, how to transmit data. These are very typical computer science questions. And the harder one is intelligence. And today we emphasize on this third phase. So let's first give a definition on intelligence, industry, AI operation. So in this talk, it refers to the status prediction of the machines or machine components so that the production, operation, and maintenance can be individualized to reduce the cost and the waste of a uniform operation. This is very similar to like user profiling, which is the basis for a recommendation system. This is a concept, a conceptual vision for a specific domain sector. Then what are the challenges and how do we do it? So let's take a look at an example of chiller AI ops. Chiller is a core component of a centrally controlled HVAC system, and an HVAC system is the main energy consumer of a building. So the key challenge is actually this is interdiscipline. So number one, you need to understand and abstract the operation procedure of an HVAC system. And this is difficult for computer science people. And you always face a challenge that you need to clarify the gain of data analytics of the AI. And this depends on data. A very common practice is that you go to a building operator or a chiller manufacturer and you ask, can you give me some data? And we will help you to improve performance efficiency, like energy efficiency. And he will ask you, what data do you want? And how much gain you can get? And you say, well, I probably first need the data, and then we can do the quantification. And he said that he need to invest resources, probably sometimes add some additional sensors. right, to get the data, and what additional sensors need to be deployed. And then this becomes a chicken and egg problem. And you need to do this in an early time, otherwise other people will publish. So we answer these challenges in our ACM e-energy 2018 paper. So let's briefly describe the operation procedure of a chiller. So this is a chiller. This is the chiller plant with lots and lots of chillers. And the chiller plant operates as follows. Given a cooling demand, find the cooling load level for each chiller. So to satisfy the cooling demand and also minimize the electricity. This seems to be an optimization problem if we know the performance of each chiller. So what is the performance of a chiller? Given certain electricity injected, find the cooling, find the output cooling power. Okay. So can we find this usually in the handbook of the specification of a chiller? Yes or no? So of course there are handbook, there are some specifications, but COP changes with a variety of factors. Then what is the existing approach? Existing approach, COP are configured to the values when chillers are first installed. The test run, okay, the pre-run of the machines before usage. This is very typical in Industry 4.0. This approach has large errors. So here is actually the blue dot is accurate COP, and the red ones are the pre-configured ones. The error is big, and also they barely have any correlation. So number two, there are lots and lots of unconfigured values. And for these values, they will not be chosen in the optimization decision making. Okay? Then we develop a data-driven approach. Given historical data samples, train a machine learning model that can predict COP with high accuracy. I don't want to say much on the specific learning algorithms. They are typical. In this paper, we identify features and develop a multitask learning approach. And we got 4-year data from 17 chillers in Hong Kong, in 3 buildings in Hong Kong. And the projected energy saving was quite significant. There were other papers developing new machine learning models and algorithms. For example, we developed a new feature selection algorithm so that we can automate the feature selection process. And other people, there are other works, for example, like in using reinforcement learning, when you need to consider the demand side and your current decision can influence future decisions, then reinforcement learning is a good choice to use. There are many other machine learning models being developed. And there are other building analytics applications as well. For example, energy consumption prediction of the entire building, not only on the HVAC system. Building integrated control. This one is about the lighting control system. And fault detection and diagnosis. Nowadays, machine learning models, data are collected, and machine learning models have been developed for various of building analytics applications. Well, new models are being developed and with better accuracy in various scenarios. But if you think about it, how exactly can they be deployed? Okay. So let's see this again, right? So this is very typical. We have new building analytics applications. That is to develop machine learning model to make better prediction and make better operation decisions. And we have clouds, right? And people are developing projects. Either from academia, you can start usually a smart city project, or there are industry players. They also develop this type of industry 4.0 projects. Currently, these projects requires usually the either employee or the scholar. They requires both domain knowledge and machine learning expertise. This is very expensive. Like data scientists alone is very expensive. And if you need them to have domain knowledge, is even more, it's very rare to find these people, right? So the productivity of the sector is very low, only emphasize on high profile projects. For example, our university has projects with buildings of International Commerce Center, actually the tallest building in Hong Kong with an annual HVAC spending exceeds $5 million US. Only these projects can afford to recruit scholars or data scientists with domain knowledge to do customized operation. Then can we make things streamlined? Okay. So from an ad hoc process to an engineering process. And if we want to do this, we need new layers of abstraction. And let's take a look at a very standard, usually data-driven data analytics process. Data collection, data cleaning, feature engineering, model training, etc. and etc. So how easy this is? Okay, let's look at a piece of data in a building. Here it is. Don't ask me, I don't know what the hell this is either, right? Actually, this is this. So it is so proprietary, non-standard, and you need the data scientists, expensive data scientists also need domain knowledge. So Break. Break is a project newly developed metadata standard that can unify the data naming convention. Okay, it defines metadata into standard RDF triples with objects and relationships. Okay. In very standard formats to unify that different buildings can have a common basis for the data formatting. And on top of Break, there is this Malta. It provides the query interface so that when you try to access data, you can write OK programs. Okay, OK programs. Still very difficult to use. Okay, if you think about it, building analytics requires data at a high level. For example, we want to do a chiller profiling, or we want to do an energy consumption prediction. We want the power data of a chiller. This can include its subsystems like a compressor, a pump, and so on and so forth, the power of them. Okay. So how do you get this data? So here is a chiller, here is a compressor, and here is a pump. These data are periodically stored in the database, sent to the database. And if you want to query this database, currently you can write a multi-query. Okay, for example, you first get a handler of a chiller. Okay, and after chiller, you get this compressor, and then you can get the data. And this chiller, you also get its pump, and then you get the data of the pump. So you write program like this. It's already better, okay? But what about another building? Okay, this is a chiller. Under this chiller, there's a compressor, and under this compressor, there is this pump. So if you write a program in here, it no longer work in building 2. It will return empty. Okay? Then you see how difficult this is. Okay, when you are trying to develop a building analytics application, you are a data scientist. What data scientists do? Okay. Data scientists need to think about whether you're using ADA Boost or whether you are using a neural network. What kind of features you need to use to develop this building analytics application, to develop a better machine learning model. At the same time, you also need to understand, to remember in your mind, what is the structure of the subsystems. And in different buildings, you probably need to write different programs, right? Oh, this is so difficult. So rare to find people like this. Also very easy to have errors in your program. So what we did is that we developed a new layer of abstraction, programming abstraction, Anagon. So we have a new Anagon QL, a new query language with only select from where. Okay, select from where. These are very typical database, Sparkle queries. So this is our objective. Okay, we want to achieve this. We analyzed a large number of building analytics applications, different applications, and we found that the basic component for data extraction for these, the common thing for these applications is that, number one, subsystems. These are usually the target for the control and optimization. Okay, like chiller, pump, elevator, so on and so forth. Number two, functionality, like temperature, power, flow rate, so on and so forth. And the data analytics applications are built on the interactions of these two components. So we define a new Anagon algebra that these two components are the elements, and they are algebraic operations, say intersection, union, differences, so on and so forth, etc. and etc. of these components. Right. This algebra can ensure properties like conflict-free. Okay. And the backend of our system is set in auto-retrieval, auto-traversal, based on an ontology, which is commonly available in the building. Okay, so we did evaluation, qualitative and quantitative. So how to write programs in Anagon? You first write a query. For example, you want to do a chiller profiling analytics, right? And for this application, you need the temperature data, flow rate data, and power data of the chillers. So what you write is temperature plus flow rate plus power. These are basically union. And then you times, this is the intersection of this chiller, and finally you will get these data, not only the chiller, but also its subsystems. Okay. And you also need outdoor temperature, so outdoor temperature intersect with the weather, right? And you put this query into Anagon, our system, and then you don't need to worry. For whatever building, we will output the data and the labels if the data exists, right? And for this data and label, then it's quite standard data scientist job. You do some transformation, data cleaning, and then you do a learning. For example, you want to use an ADA boost, then you write ADA boost regressor, and then do the learning, and then you do the evaluator. For example, you calculate the mean square error. Okay, so using Anagon, your program is much clean and also portable between buildings, from one building to another building, right? We also did quantitative evaluation. We recruited several developers and asked them to develop using Multi and Anagon, and for building analytics applications, different building analytics applications, their develop effort, the time line of code is much reduced. I have some other works. For example, we did some federated learning to protect privacy and some other optimizations. Okay, how about industry? What is their progress bar? So I'm now collaborating with some different, industry players. What are their business models? Okay, so let's see this one. That's intelligent. This is a domain expert company. So their people are mostly control people. Okay. Their business model is energy saving. Okay, so the collaboration started that I talked with some senior people in DAS, and they were very interested to see how much more energy we can save out of machine learning models. They do machine learning too, but they are not entirely confident. With them, I promote Break and Anagon. They don't care. Okay, they only care they're saving some more energy. Okay, they have their own so-called IoT data management ecosystem, and that's proprietary, and they don't want to use open source Break. These are very common for our CS people. And I also collaborate with a computer science company, a low profile but very world leading company. What is their business model? They are interested because they are developing like smart district, smart theme park, smart city projects, and they want more and more smart elements into their project. And this is why they want to see whether we can contribute an element into their overall project, right? And also work with IBM Hong Kong and the government. Of course, in this type of project, they also want to save energy. But from the government's viewpoint, they are more open to innovations. Actually, they always ask us, do you have some extra innovation that we can put into the project? And by this way, they are more open to system like Break and Anagon, these open source ecosystems. Note that this system cannot directly save energy, right? So, okay, now as a summary, I think in this talk, we shared some experience working in an interdisciplinary area. The important thing, first important thing is to understand and model the operation procedure, and that is quite challenging. Initially, there usually is a chicken and egg problem. Okay, you're asking for data, and they are asking you how much gain can you provide with certain type of data, which is quite difficult to answer before you have the data. And second, from software's viewpoint, developing abstractions can hopefully can help to shape the industry. Actually, even if you talk with the domain expert company, after your discussion with their senior people, you talk with their frontline engineers, collecting data and cleaning data is not an easy job. It's a headache. So I think that developing easy to use software needs more and more abstraction, and hopefully that data scientists can do the job of the data scientist and domain expert can do the job of the domain expert. And finally, the industry, at least in my area, in the southern part, in Hong Kong and in the southern part of China, I would say the industry is still ad hoc. Okay, different people have different perspective, and so are opportunities. And by this, I thank you and welcome for questions. Thank you.
Thank you, Dan, for the talk. We have a couple of minutes for questions. Again, feel free to put your questions in the chat, or if you have access to the Slack channel, you can write your question there. I can either call your name, unmute yourself and ask your questions, or I can just read your question and ask it from there. Okay, so while we are waiting for the first question, I wanted to ask you then about open data that might be available from buildings. So, as you mentioned in your talk, one of the main barriers to building analytics and also trying different machine learning models, evaluating them on a large number of buildings is the lack of data. And we have worked with different companies in this area, and we know that they are very conservative when it comes to sharing their data. So, in your experience, what was the main challenge in getting access to data and convincing these companies that you will not be able to use this data to run, let's say, unwanted inferences on the buildings?
So sorry, it's not entirely clear at my side. Can you briefly explain that your question again?
Yeah. So I was asking about open data. Can you hear me now?
So open data, right?
Yeah, open data about buildings. So how much open data is available, and would you be able to, for example, convince them to share this data with the rest of this community to be able to build different applications on top of their buildings?
I think this is a very good question. I think for these two, the first stats and this SIS company, I don't think they have the incentive to share data. Well, it's extremely difficult uh, because of not only privacy but also confidentiality. And also, they are not ready mentally. I mean, that they always think that their data has additional values. Uh, then, when you talk about the government buildings, they are more open. They're more open. Okay, and we are currently working with them, educating them that they can share certain data and open to use. For example, we told them that we can develop a competition. Okay, you open some data, you share some data, and we can develop some competition and ask some high school students to join. Uh, then they are better. Okay, they're better in that position. But now I think for the first two kinds of industry players is extremely difficult. Yeah, that's my experience for the time being. Even you say that you can handle the privacy or confidentiality, it's still difficult. Yeah,
Mhm. Okay. Thank
it
you
needs
very
some
much.
time. It needs some time to get things ready.
Mhm. And were you able to, for example, control a real building using your algorithms, or it was mostly done in simulation?
Okay, this is another very good question. I think for the first two, for this one and also for this government, for the first one, actually after we hand them the model, they are currently using it. Uh,
Mhm.
and that is because the building is a newly established building and is still in the testing and pre-run period. For this type of building, it's easier. For existing buildings, that's difficult. If you want to interrupt their existing operation procedure, it's very difficult. And again, we need government. Okay, these people are more open for innovation, and Hong Kong government has a pressure of competition with Singapore government. So they after they have this pressure, they are more open to to allow people to control. But we are still not there yet. We are working on it.